So we're going to look at the Fourier series approximation to square wave. So we're going to be using the same square wave that we generated in the graphical calculator. So we'll work out the values for the coefficients A0, AN and BN, and once we've worked those out, we'll go back into the calculator and we'll put those values in and see whether it works. So we've seen the Fourier series there as approximation of a function f of x using a series of other functions. And we have to try and figure out what the values of A0, AN and the BNs are. And we've seen from our derivation in the previous videos that we can work out our values of AN given by this here, and the BN from this, and the A0 from this. And these are our inner products. So let's look at the function here. So the function is just a little square wave. It's only defined between minus pi and pi. Whenever x is greater than or equal to 0, the value of it is going to be 1, and whenever x is less than 0, the value will be minus 1, and that's it just written there. So we're going to work through this in full detail in the next video, the next slide here, but it's going to be a lot of maths in it, but we'll be able to simplify it, and I'll show you it derived in a much simpler fashion. Okay. So here we go. This is the full derivation here, and again it does look quite kind of yucky, but we can simplify it. But I'll work through it in detail first. It's worthwhile just to see it done fully at least once. So we can say that A0 is equal to 1 upon pi times the integral from minus pi to pi of f of x by dx. Now the value function f of x is actually split into two. It's minus 1 whenever x is between minus pi and 0. And it's 1 whenever x is between 0 and pi. So we do that integration there, and that gives us minus 1 upon pi of x from 0 to minus pi plus 1 upon pi x from pi to 0. So put the values for pi and the 0 in, and that will give you a value of 0. So the value of A0 is equal to 0. Now you don't need to take my word for it. You should go through and just confirm that for yourself by going through that maths yourself. Now we want to work out the value of AN, so the ANs are equal to 1 upon pi times the integral from minus pi to pi of f of x cos nx by dx. And again it's split into two. There's a value of the function of minus 1 from minus pi to 0, and a value of the function of 1 from 0 to pi. And whenever we work through that integration, we get this line here, and we put the values in, and it gives again a value of 0. Again, go through that yourself and check and make sure the maths looks okay to you and you agree with that. So all of the ANs disappear. So let's look at our BN. So our BN is given by the sin nx term, and again it's split into two. So there's a value from minus pi to 0 of the minus 1 sin nx by dx, and there's a value of from 0 to pi of the 1 times sin x dx. Now whenever we integrate that, we get our 1 upon nx cos nx from 0 minus pi minus 1 upon n pi cos nx from pi to 0. So we can take out our common factor of 1 upon n pi, and that gives us this line here. And next line here is important, because whenever we put the value for say 0 in for x here, it doesn't matter what value of n is. When x is 0, that's going to give us a value of 1. Now whenever we put a value in for minus pi for x here, well, cos of minus pi is minus 1. But that's for a value of n equals 1. Whenever n equals 2, that would be minus 2 pi. So the cos of minus 2 pi is plus 1. And for n equals 3, the cos of minus 3 pi is going to be minus 1 again. So it's going to change from plus 1 to minus 1 to plus to minus to plus to minus. So it's going to be equal to minus 1 to the power of n. So that's important, so that you notice that cos nx for x equal minus pi and n as an integer is written as minus 1 to the power of n, because that crops up quite a lot in the Fourier series. Now we do the same for this term here. We get this one, and when we multiply out and we gather all our like terms, it gives us 2 upon pi times minus 1 to the n, all times minus 1 to the n plus 1 upon n. Now if you put in a value for n equals 1 and a value for n equals 2, then you'll find you'll get 4 upon n pi and you'll get 0. So all of the n terms being odd will give you 4 upon n pi, and all the n terms being even will give you a value of 0. So it means that our a0s are 0, our ans are 0, and all the even terms of bn are equal to 0. So all we're left with are the odd terms of bn, which are going to be 4 upon pi times the sine x, and it's going to be sine 3x upon 3 times the 4 upon 5, sine 5x upon 5 times the 4 upon pi, and sine 7x upon 7 times the 4 upon pi. So this is our approximation that we've been looking for, and these are our values for our a0s, ans and bn's. So the only values are the odd terms of bn, and these are the values here that we've been looking for. Now that's a bit of a mouthful, a lot of maths there, and we can actually simplify it, and we can simplify it if we just note a few things about the symmetry of the problem that we have. So I mentioned in a previous video that the evenness and oddness of our functions and the symmetry of our functions is quite important whenever we're working through these Fourier series. So here's an example here. Whenever we try to find this value of a0, we notice that we're integrating a function f of x. Now the function that we're integrating here, if we note, it's a purely odd function. So we're integrating that from minus pi to pi, so you could look at that, you can say if we take the area under here and we add it to the area under here, this area will cancel out with that area, will give us a value of 0. Equivalent, we were saying, when we integrate an odd function between these 2 points, between two symmetric points, we're going to get a value of 0. So straight away we can say that a0 is equal to 0, so we don't need to go through the first part of trying to work out what a0 is. So we didn't need the first part of our analysis that we just did in a couple of minutes ago. So if we were to do the same thing with the an, we would notice that a cos nx, that's going to be an even function, and we've seen that f of x is an odd function, so we're multiplying an even function with an odd function. When you multiply an even function with an odd function, you get an odd function. And again, when we integrate that odd function symmetrically between minus pi and pi, we're going to get a value of 0. So we'll be left with the same situation we had here of integrating an odd function. So we can say straight away that all the ans are going to disappear. So we didn't need to bother going through the analysis of trying to find out what all the values for an are going to be. Now there's one other thing here to note, is that in this case here, for the bn's, we've got an odd function, and the odd function is going to be multiplied by this here, which again is an odd function. When you multiply two odd functions together, you get an even function. So if I was to integrate an even function between minus pi and pi, well, that would be equivalent to integrating twice the function from 0 to pi. And you can see that if you just draw it down. Maybe I'll put it down here in a little graph. So you can see here, all we would be doing is, instead of integrating the function here and getting this area and that area, it's just equivalent to integrating just from this point to this point and multiplying it by 2, because you're going to get 2 times the area. So we see that there's several ways of simplifying this down, and we'll go and we'll look at the final derivation, which has been done in a simplified manner. So here's the simplification. We know that a0 is 0, we know that ans are 0, we need to find our bn, but we don't need to integrate the bn between minus pi and pi. We can integrate the bn between 0 and pi and multiply it by 2. So the function here will just be 1 times sine nx by dx, and when we integrate it we get this here, and again whenever we take the limits we get this equation here, and again if we put in our values for n is even and n is odd, we'll get our 4 upon n pi, we'll get our 0, and that will give us our value for our Fourier series approximation to the square wave, which is given by this equation here. So I think you can agree that this here is a lot quicker than what we did in the previous page. So now let's take all of the values here and we'll go and we'll put them into the graphical calculator and see whether this all works. So let's go now and we'll put our values into the graphical calculator and see if we can approximate the square function. So you've got a copy of this in the resources section, so I suggest you open it up and you can go along with this as well. So we've got our square function there is equal to 1 from 0 to pi, and it's equal to minus 1 from 0 to minus pi. So let's go ahead and we'll put our values in for our Fourier series coefficients. So first of all I think we can have a look at the Fourier series. So that's our Fourier series there, goes up to our B5, okay. What's that equation here? So let's go ahead and we'll put our values in. Now I'll get rid of my image so you can see more of the screen. Okay, so we know that our n's are n equals 1, 2, 3, 4 and 5. We know that our a0 is 0. All our values of a1 and a2, all our values of a are going to be 0 as well. We've only got odd terms in the b's, okay, so the b, the first value is going to be 4 divided by pi. So that's our first approximation. Our next approximation, there's no b2, so it goes up to b3. So b3 is going to be 4 divided by 3 times pi. And that's our second approximation. You can see it's starting to tend towards that square function. And finally, the last one we're going to put in is our 4 divided by 5 times pi. So there you go, that's our terms that we've added in. You can see it's starting to approximate that square function. The next term we put in would be 7 and 9, so we would have 4 upon 7 pi and 4 upon 9 pi, and it would gradually get closer and closer to this square function. So you can see it works, and it works quite well. Now I've got another simulation there that I'm going to show you, and I'll bring it up, and it will show you the approximation using a different sort of graphical approach. So here's another graphical representation of the first, the third and the fifth harmonic in summing up to give us that square function. So I'll move this along a little bit. Now it's quite a busy little diagram here, so I'll try and explain it. We've got this line here in black. Now that's the first, or the fundamental frequency, and that's a phasor just rotating round at the fundamental frequency. This little red one here is a phasor rotating round about at 3 times the fundamental frequency, and this little pink purple one is rotating round at 5, the fifth, 5 times the fundamental frequency. So those are all rotating round about. Now what I've done is I've taken this one here and I've added it on to the end of this point here. So we're just summing these phasors up vectorially, so that one goes to there, and this phasor here gets added on to the end of this point here. So we get this little single point here, and our contention is then that because we've added these up vectorially, this point will map out the approximation to that square function. So you just need to follow this point. So this point here is basically the height of this little point, and it will map out the square wave. So we'll let that run along, we'll see it happening. So you can see that height, it's mapping it out up and down. You just follow that little blue, follow this little blue dot here, and it'll map out this square function. So there you go, and it gets round to the minus 180, and you can see that all the phasors will line up. So you can see them all lining up here, and then they're heading back round the other direction, and it's continuing to generate the rest of that square function for us. So that's a nice little graphical representation of what's happening, and you've got access to this as well, so you can get this out and have a little look at it. Again, it's a little bit busy, but it does show or give an indication of what's happening here. So that's all for this video. I hope it was of use, and I'll get you on the next video. Goodbye.